Yes, let's go on to our next speaker now, and it's Professor Marcilio Alves from the University of Sao Paulo in Brazil. Welcome, Marcilio. Marcilio is an associate professor at the University of Sao Paulo, an editor and founder of the Latin American Journal of Solids and Structures. He's the author of some 100 articles and of a book, Impact Engineering, Fundamentals, Experiments, and Nonlinear Finite Elements. Marcilio got his PhD from the University of Liverpool, possibly in 1996, I'm guessing, but around there. Over to you, Marcilio.
Okay, thank you much, Wesley. I'd like to thank you, the organizers, Sarah, Rafael, and Mohamed, for the invitation and the organization of the meeting. And I'm going to share my screen now, and then I start my presentation. I hope you are seeing it. And so first of all, this is my university here, overview of University of São Paulo in Brazil, state of São Paulo and city of São Paulo. The city is in the back there, you can see. And the topic I'm going to talk a little bit today is dynamic material characterization, but I'm going to make a bridge between this topic and the use of the information of material characterization in components, in the study of components. So as you know, nowadays more and more the digital image correlation is being used, and we are also adept of this technique. Now in the past we had lots of clip gauges, strain gauges, and so on, but we are using quite a lot digital image correlation for even 3D, for material characterization and localization and so on, as you can see in these pictures here. And with the material characterization, we are also using optimization. So that's a technique also we are introducing in our lab for us to do this force displacement to match with the experimental one after a few runs, and then we can infer the stress strain curves for materials that are sometimes difficult to measure directly on the specimen, like when the specimen or the body we are testing is too small. And also a topic that we've been studying more and more is failure. And in failure in metals, we have this mechanism of shear, fracture, and fracture due to void formation, and this is affected by triaxiality. So it's quite common in the past and still nowadays using notches specimens as we are using here, but also we are using different geometries to induce different stress states, like when we have high triaxiality here or low triaxiality here. And on the left side of the images, we have a digital image correlation field. And on the right-hand side, we have finite element simulations, showing that we could get a good match. And from this, we can get information from the stress and strain field to apply to our failure criteria. We also developed a different specimen that we've been presenting here, where we have, we call double failure, where when I pull this specimen, it breaks here and it breaks here, as you can see on this simulation here. And we have this load being going to the top, and then one part of the specimen breaks here first at high triaxiality, breaks second at high triaxiality, and at low triaxiality, it fails here by shear. So in a single test, we can induce different modes of failure, and the curve is also very hard to be captured by a finite element analysis, because the test is quite elaborated, and we trust that this is a specimen that could be used by our colleagues in assessing failure. So then here is some geometry, and this has been published, and then you can get the publication with my name, searching for my name. We also have in the lab torsion tension machines like this one. We also use these machines for inducing different stress states with torsion on play. And then this draw my attention to make the comment that there is a demand, in my point of view, of a more complex loading regimes. And then with these specimens, we can, with these machines, we can get to these more complex regimes. Oops. Let me go back here. Here. This is a machine that Rafael has developed in part of his PhD, where we drop the mass on the top of this rig here. It's 2 meters high, so with there is a laser here, and then there is a load cell in the bottom here as well. You can see here, and then we can pull the specimens at the mid strain rate. So instead of jumping from low strain rate to split Hopkinson bar tests, we can also do mid-range strain rates, and then we can get good information of the material behavior. And as for high strain rates, of course, we use Hopkinson bar. We designed our own Hopkinson bar in the lab. It can operate in tension and compression mode. This is a figure in tension mode. And then we can reach strain rates. In fact, we can reach strain rates closer to 10,000 per second in our equipment. Although we had designed this machine relatively large, of some 6 meters long, perhaps, I would advise nowadays to be for people to be more involved in the design. This keeps popping up in the design of small Hopkinson bar machines. I think it's quite interesting. This is the compression of a ring. That's a study we made where we had shown that rings can be used to the benefit of decreasing the influence of friction when we do compression tests. We did lots of mathematical modeling for us to reach the conclusion that we can get information from the equivalent stress curve of the material in compression using a ring and avoiding friction influence. And also going more a little bit now to components. This is, of course, is a metallic tube under buckling mode. It's a good quality picture, so then I put here to show you that we are able to launch in our laboratory with a drop hammer. We have up to 1 ton of masses from a height of 6-7 meters, so we have a lot of energy at our disposal. And we can also do tests as we did for metals. We can do also for as we did for composites. This is a quasi-static test, but we also did for dynamic testing in this fiber metal laminates and on the composites, carbon fiber composites tubes. And also these required material tests on these composites. So we made a special rig that we published on Composite Structures, where we were sure to get a very well-defined shear stress state or strain state too, which can then be used later for numerical simulation that we had also done in a paper we just published now. So then we were involved on the simulation of carbon fiber tubes under axial impact, considering friction, delamination, in all the features present in this phenomenon. We also did tests on a very complicated, complex structure or a component, which is a tire. This has been done many years ago, but I just bring to you here to show that we had all this process of geometry definition, material definition, and we did the numerical simulation comparing relatively, or actually comparing very well with the experiments. We also had capabilities to do high-speed tests that we are doing now. I couldn't bring to you yet because it's just on the lab now, but we are doing launching cubes on panels where we had at very high speed, 300 meters per second, 200 meters per second, where we had to hit the target with the edge of the cube. So that's a very difficult test to be done, but we are capable of doing so. Yeah, this is a slide which sort of summarizes what Rafael had made during his PhD here, together with Cantwell in Liverpool too, where we had tested these panels which had fiber and laminated also with aluminum. This is our gas gun in a setup, in a vertical setup. This is our drop hammer here. So we established the ballistic limit, but also we established something that's very difficult for this test, and this is thanks to the effort of Rafael, where we measure force against displacement using a laser system. So that's a very difficult curve to be obtained, and we managed to do so. These are some details of the numerical simulation that we did for these composites. And my question before about helmets is that because we also are connected with the design of helmets for motorcycles, and in Brazil, we have a very large number of victims in traffic, in road accidents. So we are now about 35,000 people dying every year. So quite high number. And it's decreasing a little bit along the years, but motorcycle accidents is a very important cause of death and permanent disability. So we are involved on tests of helmets, as we have here this big, also designed here in this case by Rafael. So we did lots of tests to be sure to meet the protocols of United Nations and the protocols of Brazilian regulations. And so then it's a contribution that we are doing to the society to have better helmets. And then that was my question before related to helmets. And well, this is a picture that I took in Munich, but it brings up the topic of scaling. So we did lots of tests on scaling. So, but I learned a little bit more today with Cantwell about his work. And so we were able to capture also very good, make a good correlation between scaling of a large beam and a smaller beam. As we can see here, the collapsed curves between the blue and the black, which is a model in a prototype, so to say, was quite good. Where the red is, the red here in the case is just applying the normal scaling laws for this test, and we had to correct these scaling laws in a particular way, so to get rid of the influence of strain rates. So then, or not to get rid, but to consider strain rate effects, and then we can get this good match between black and blue curves, in the same here as well. And this has been used, this scaling knowledge, to test very large plates, as we did here for 1 ton mass, and would be much better to test small scale, like this model of 8 centimeter side. So then we are able to make a comparison between this very difficult test to be made with 1 ton and this, I don't remember now, but a few grams only. So there is a similarity here that we tested in a factor of 100 in terms of scaling, so a very large factor. And then we applied this for the ship collision. This is a project we had. Of course, in the beginning, to make matters easier, we tested on the lab. So we make a model of a real ship with a factor of 100. Instead of calling N, as Wesley called, we call beta, this factor. So this is a factor of 100. And we did also a test of one ship hitting the side of another ship, as set here. And this is the setup we made. And then we were able to, of course, to record everything. And then we did this test in a model, but we wanted to expand the results to a real ship collision. And of course, we did this with finite elements. And first of all, we had to show that we could model well the tests in the model, as we can see here. And then with the scaling laws that we had been developed in our lab and has been published in quite a few papers, we are able to go to the real physical space of 1-to-1 model. So we also took care of welding. That's an issue, very complicated one. And also in order to cooperate with the society, we developed a little car that we wanted to make it safe according to the UN regulations, which are tougher than the regulations in Brazil. So we made a urban car for 2 people, and we used meta model, which is also a technique that has been used more and more, even now in industry, but we have in the laboratory now softwares and so on, where we could assemble a meta model for this car. I'm not going into the details here, but we are able then to perform and to design the car for impacts, frontal impact like this one here, and lateral impact like this one here, and lateral impact with airbags and without airbags. So we studied also airbags, which is quite demanding in terms of finite element. The number of the degrees of freedom increase a lot and so on. And then we tested the UN regulation and the NCAP regulation. We also made a rendering of our car. So we are actually redesigning a few features that we wanted to improve. And we are also building the car, which is going to be an electrical car. We also did this pole test, but I brought this simulation here, especially in connection with the next one that I'm going to show you, to make a general comment, which is, if you can notice, the impact on a pedestrian, but the pedestrian is an actually human body model. So it's not a dummy model. So then we get access to this model. And then, we got access to this model when we can study now the tendons, the femur behavior, the neck, arms, and the head. So then we have interest in connection with the helmet. We have interest in the head behavior as well. So then this is 2 million degrees of freedom or more for this fellow, let's say. And we also have children or a child size, a more chubby man and a woman. So these models then can be used now in connection in tests that we wanted to guarantee a good behavior like this one. So that's quite different, the behavior of a human body with a dummy model. And then we wanted to explore this in our research activities. Lastly, I bring to you also an issue that is very important and sometimes is overlooked a bit, is friction under the conditions of impact, especially in the automotive industry. So we developed a rig which measure the friction coefficient according to the main variables that are of our interest, which is the slip rate velocity, the slip rate, the contact pressure, temperature we didn't take into account, but we explore also, basically contact pressure and slip rate. And then the coefficient of friction changes drastically when these variables are changed, are altered, and then this shows to us that we cannot use a single coefficient of friction. So then we need to measure, put in a model to make identification, and then we had to develop a special machine to do this friction. So part of the examples and applications I showed here were from my book. I just published this year. This book, it gave me a headache of producing it along many years. So, but I hope now I came to a very good summary of what the impact field, impact engineering field is, and also at the end, so you can get it at Amazon. And at the end, I'd like to thank you, the organizers. I hope I had written and translated well the word thank you in Arabic, and of course that's I translated well. Thank you in Portuguese, which is obrigado. So thank you very much.
Obrigado.
Thank you very much. That was very good. Thank you, Marcilio. We have a few minutes for questions. If anyone would like to ask questions.
Professor, sorry, go ahead, Professor Guan. You are my supervisor. I can't go before you.
So I have a very quick question regarding motorcycle, helmet. Apart from impact behavior or impact resistance, do you do any kind of thermal comfort research?
Thermal comfort?
Yes.
No, but I learned today that thermal comfort is an issue, so that can be considered on a model, but so far we didn't do any investigation into this field. But in Brazil, of course, this is an issue because it can get hot in summertime.
Yeah.
So then that's something to be considered. Yes, for sure.
Good.
Thank you.
Dr. Mohammed.
Yeah, Professor Marcilio, thank you for your presentations. I have a question about the bullet or the balls that you show us. You shot it in the panels with keeping temperature. How you keep temperature fixed?
Oh, the temperature is not fixed at all. So the temperature rises when there is the contact between the bullet, the sphere, and the plate, and this is natural in the phenomenon because I'm going to change the kinetic energy at the end of the day also in heat. So then the heat increases a lot, and this should be taken into consideration by any constitutive law that we are going to use for the simulation. But for the experiment, there is no way, or at least I don't know, no way to change, to keep the temperature constant.
Okay, thank you. Clear.
Any further questions?
Maybe Rafael has a question.
Yeah, go ahead.
Yeah, just a quick one. Regarding the friction, Professor, do you have any model that can cover these changes in the feature, the friction as the slip rate changes? Nothing comes at the moment.
Yes, we had developed a constitutive law that takes friction as a function of slip rate, pressure, not temperature. And then the fitting of this law with the experimental parameters allow us the identification, and then we use these constitutive laws in the simulation of the dummies inside the cars, because the dummies inside the cars, in an accident, they move and then they slide along the seat belts or in between the face of the dummy and the airbags and so on. So this is considered in our model, yes.
But what about the influence of these friction parameters in the result in terms of, for example, acceleration in the head, contact forces?
Oh, it's quite evident. So then the brain damage, for instance, or the head injury criterion is affected significantly if we used one or other friction coefficient. So then that's why that's an important issue that needs to be taken into account.
I thank Marcilio once more for his very interesting talk there, and thank you very much, Marcilio.
Thank you, Wesley. Nice to see you again on the screen.
Thank you, sir.
Bye, everybody.
Okay, thank you.